For question 3.13. So the first thing we are going to do is to draw our free body diagram. We are going to label A, B, C. Okay, so our question says it is known that the connecting rod AB exerts on the crank BC a 2.5 kilonewton force directed down and to the left along the center line of AB, determining the moment of the force about C. So we are told that a force of 2.5 kilonewton acts along the center line AB. So we are going to convert that to SI units, which is going to be 2500 kilonewton. So we are going to draw this to indicate that 2500 newton. So the next thing we are going to do is we are going to take this in two ways. We are going to draw our uh, horizontal and vertical components. Then, because of the application of the principle of transmisibility, which tells us that if a force is acting along a rigid body, along a straight line on a rigid body, then the force can be taken to act along any point on that rigid body and it will have the same effect. So this means that whether our force is acting at A here or acting at B here, it will have the same effect on the rigid body. So we are going to solve this question in two ways. We are going to take the force act when it is acting at A and when it is acting at B to see whether we are going to get the same answer. So for the first part, we are going to take it as acting at A and look at what we are going to get. So if it's acting at A, we are going to have horizontal and vertical component, like I said. Then to do that, we need to get our theta here. Now to look for the theta here, we need if we incorporate the distance that we are given here, you know that from here to here, this is 144 mm. But we are going to convert it to SI unit also. So that's going to be 0.144 meters. And here to here, 0.056 meter. And here to here, we have 0.042 meter. So we know that our theta here is equal to this point also. Uh, So this point is also equal to our theta because this is a straight line and this line here is parallel to this here. So we're going to, this theta will be equal to this. So we can extract this right angle triangle. We can extract this right angle triangle and calculate our theta because we have this distance and we also have this distance. So if we extract that, we're going to have something like this. Theta, then here 0.144 meter, here 0.042 meter. So we're going to use our Tokatwa rule. So because we have opposites and we have adjacent, we're going to use our tan. That's that theta is equal to 0.144 over 0.042. And theta is tan theta 0.144 over 0.042. Our theta should give us 73.74 degrees. So with this now we can write our vertical and horizontal component as A as 25, this point here, 25 sine 73.74 degrees for our vertical component. Then here 25 cos 73.74 degrees as our horizontal component. So after this, the next thing we are going to do is to look for the moment, determine our moment, which is going to told us that we should determine the moment of the force about C. So after having our vertical component and horizontal component of this 2500 Newton force, we can now calculate our moment. Formula for our moment is R times F, where our R is the perpendicular distance and F is our force. So for the moment, it's going to be a sum of the this this moment of our vertical component and our horizontal component. So for the vertical component, the first thing we need to notice is that for moments, anti-clockwise is always positive. So we need to take note of this. For moments, anti-clockwise is positive. This is very important in our solution for moments questions. So for the vertical component, it's going to be, we need to determine whether it's going to be positive or negative. So for the vertical component, is if we have C, let me draw that again. C and A, B. So if we look at C here, to calculate whether it's going to be positive or negative, we are going to imagine C here because we are taking the moment of the force about C. We are going to imagine C here is nailed at this point, and our ABC is a rigid body. So if it is nailed at C, and we have a force here, that is for the vertical component first. If you have a force acting at A vertically, in which way is it going to move our rigid body ABC? So if this force acts along this path, we can imagine that if the magnitude is big enough, it will tend to change the position of this our rigid body ABC in this way. Initially, we can have, if you have the body here, if you have our body here, and this force starts acting on it, then you can say the body can move this way here, then next here, then here. It means that if we have a force acting vertically, it will tend to bring our rigid body ABC down this way in an anti-clockwise position. So because this force is acting vertically downwards, it's going to tend to bring our body this way in an anti-clockwise position. So because it is anti-clockwise, our symbol here is going to be positive. So I'm going to write that plus. The next thing is to calculate R, which is the perpendicular distance between A and C. And because A and C, A is acting in a straight line alongside a straight line with C, our perpendicular distance has to be 0 because the way to calculate it is this. If you take the force, you can draw a line. You can look at the straight line which this force is acting, that's A. Then we are going to take a parallel alongside like the same path with our C. You can do that this way. If you say A is here, A is acting along this line, then the parallel we are going to take at C is going to be along that same line. Then we are going to look for the distance between the two. Something like this. A B C. A B C. A acts this way. They are going to take a similar parallel at C. Something like this. Then we are going to look for the distance between them. But because if you look at our question here, we can see that A acts on the same line as C, which means that the distance here between here and here is going to be zero. So there's no difference between the line of action of these two. So our perpendicular distance here is zero. We're going to write zero. Then we're going to write our force. Since we're calculating for the vertical component, it's going to be 25 sine 73.74. Then we move on to the horizontal component here. So we are going to do the same thing for this. So we are going to look for the symbol of our calculation. Then is it going to be positive or negative? We do the same thing. We take this, draw it here. A, B, C. Then we have a horizontal, the horizontal force acting along here. Then if you look at this, if this force pushes, if the horizontal component pushes our point at A, like we said, with this point C, if it is named here, we have a force pushing A horizontally this way, in which way our rigid body ABC going to move. So if the magnitude of this horizontal force acting at C is large enough, then we can see that our body will move along this way. If this is the initial position, then we can have the next position this way. Then if it pushes it again, we have this way, like this, like this, like this. So you can also see that this horizontal component is moving our body in an anti-clockwise position. So for our symbol here is going to be positive also. Then the perpendicular distance. You look at we take the parallel along A along the force, then a similar parallel at C, a similar parallel at C. Then we look at the distance between them. And according to our diagram, that's going to be is you have here 0.144, you have here 0.056. So this position will be 0.144 plus 0.056, and that should be 0.2 meters. So 0.2 meter will be our perpendicular distance. Then we are going to write our force. That's 25 cos 33.74. Then if you calculate that, we should get, because this is 0 plus 140. the solution give the solution should give us 140 Newton meter. And like we said, for moments, if it is positive, it is anti-clockwise. So since we got a positive moment, we can write our symbol for anti-clockwise this way. We can draw it this way, which means the moment of the force about C gives us 140 Newton meter. So the next thing we are going to do is to take our force acting at B. Like we said, given the principle of transmissibility, if we take our force acting at A, and if we take that acting at B, we should have the same thing. So you have demonstrated it acting at A. And the next step is we are going to take it acting at B and see if we are going to get a similar result. So for the same question, 313, we are going to take it acting at B. So we are going to draw a free body diagram A, B, C. Then if our force is acting at B this way, 25 Newton, then the vertical and horizontal components. So the calculated previously, our theta is 73.74 degrees. Then we can write out our horizontal vertical components as 25 sine 73.74, 25 cos 73.74. So we can draw our distance here, 0.056, 0.144 meter, then 0.042 meter. So to calculate our moments, and our formula R times F. So the first thing we are going to take is, let's take a look at our vertical components and look at the direction in which our force is going to act. So we can draw that out. A, B, C. If you have this force acting this way, like we said, we are going to take this C as nailed here, and we have rigid body A, B, C. If it is nailed at C, and we have a force acting at B, in which way is it going to tend to move our rigid body? So if we have a force acting at C, we can see that if this force is applied, we can expect our body to move this way from this initial position ABC. If the force act at B, then we can expect our body to move this way. Then if more force is applied this way, this way. So we can see that our body here is also moving in an anti-clockwise direction due to the application of this vertical force at B. So we can write as, since we said before that anti-clockwise is positive for moments, we can write our position, our symbol as plus, since it's moving in an anti-clockwise position. So plus, then the next thing is our vertical, our perpendicular distance. So you look at the distance from, I'm going to draw a parallel here, draw a parallel here, and a parallel at, a similar parallel at C. So the distance between them is going to be, if you look at our diagram here, you can see that if you have a vertical force at B, and if you draw a similar parallel at C here, you can see that the distance is going to give us 0.042 here. So we can see here 0.042. Now that's going to be our distance. I'm going to write it here 0.042. Then I'm going to write our force. That's 25 sine 73.74. Then we're going to move to the horizontal component here. So we're going to do a similar thing. Let's draw our free body diagram A, B, C. And here we're going to take a look at the horizontal force acting at this place. So if you have a free body, a rigid body ABC here, and an horizontal force acting at B, in which way is it going to tend to move our body if it is rigid at C, if it is nailed at C? So if you do a similar analogy here, we can say that if this body is initial position ABC with this force at B, you can expect our body to move this way. Then if more force is applied, you expect it to move this way, like this. So as you can see also, it is moving in an anti-clockwise direction, which means our symbol is going to be positive. So we are going to write plus, then we have to look for our perpendicular distance. So same way, you can see here, we draw a parallel for this force acting here, and we draw a similar parallel at C. Then we look at the distance between them. So as you can see from our initial drawing, that this distance is the distance that is here, that's 0.056 here. So you can write our distance here as 0.056. So we're going to input that in our calculation 0.056. Then we're going to write our force 25 cos 73.74. So we are going to solve that. Then we should have 100.8 plus 39.2. If you calculate that, we should have 140 Newton meter. Then because it's positive, you can draw our symbol 140 Newton meter. So as you can see, whether we take our force acting at point B or point A, you can see that we got the same answer of 140 Newton meter. So which shows that the principle of transmissibility is verifiable.